Good afternoon. Today we'll see about one more memory reducing technique, that is computational variables. Okay, so it is one of the memory reducing techniques. Previously already completed one memory reducing technique, that is redefines. Right? By using redefines, we are reducing the memory. One more variable is to for reducing the memory is computational variables. It is one of the memory reducing techniques. It is only for numeric variables only. Only for numeric variables. So we can compress the memory and store the number of digits. We can compress the memory and store number of digits. In computational variable, the data will be stored in form of binary formats, internal floating point, and packed or hexadecimal formats. Binary means we already know in this binary format, like zeros and ones are the binary format numbers. So in computational variables, the memories are and the units are bytes, nibbles, half word, full word, and double word. 1 byte is equal to 8 bits, and 4 bits is equal to half word, means 1 nibble. 2 bytes is equal to half word, 4 bytes is equal to full word, 8 bytes is equal to double word. Okay. So there are 6 types of computational variables: comp, comp1, comp2, comp3, comp4, comp5. In the comp, the data will be stored in form of binary format in comp1 and comp2 internal floating point, comp3 packet decimal, again comp4 and comp5 binary formats, zeros and ones only. Clear?
Yes,
Now,
ma'am.
Yes, Mani.
coming to computational variable, so it is one of the memory reducing technique and a computational variable. So here data will be stored in form of binary formats. The variable declaration is, so what is the declaration we have seen previously, like level number, variable name, picture class, data type, size, value class, and assign value. Similarly, computation variable declaration is like level number, variable name, picture class, data type and size, up to here same. So we'll add usage and what is the comp we are using. Okay. And value class assign value. This is the variable declaration for computational variables. Okay. In computation, in comp, the memory calculation will be based on the following range. What is the range? For numeric, what is the maximum range? 18 bytes. Okay. Here will represent S for the computational variables. S means signed data type. Okay. So numeric from 2 bytes to 4 bytes, it will take 2 bytes of memory, means half word, and numeric 5 bytes to 9 bytes, it will take 4 bytes full word, and from 10 bytes to 18 bytes, it will take 8 bytes double word. This is the range for computational comp, only for comp. And there is no memory for the signed data type. S is what? Signed data type. Okay, there is no memory for the signed data type. Clear up to here? Hello.
Yes, ma'am.
Yes, Mani.
Yes.
Now we'll see the some examples on comp. I'm declaring a variable 01 WSA with signed data type of numeric with 4 bytes comp. So it will represent how many bytes? 2 bytes. So display WSA memory of WSA. So by using length of, we are getting the picture class length size. By using length of only, no, we are getting the memory of the picture class. We completed the length of concept now.
Yes, ma'am.
Length of WSA, we'll get 2 bytes memory in the output field. So we are using length of no. So it will, in the output area, it will represent with 9 bytes of memory. Okay. Will
Yes,
represent
ma'am.
8 zeros and 2 9 characters of bytes of memory in the output. Okay. So if you don't want these previous zeros means, so you can add one more variable L and compute L equal to length of WSA. So your length of WS will be stored into L variable. L picture class length is 2. So what is the S9 of 7 comp? S9 of 7 range 5 to 9. It will represent 4 bytes. So in the output you can see 4 bytes of memory only. Okay, clear?
Yes, ma'am.
Hmm. So third example, one more variable with S9 of 11 comp. What is the S9 of 11? From 10 to 18, it will represent 8 bytes. So again, I don't want extra zeros. So my picture class length is L is 2 bytes. Compute L equal to length of WSA. Display memory of WSA is L. It will represent 2 bytes of memory. It is 808. If you write here 1, okay, if you write here 1, it will represent only 8. Clear?
Yes,
No?
ma'am.
So I'm declare one more variable. S9 of 4 only com. One more variable L. I want only 2 bytes, 2 bytes of result only. So compute L equal to length of WSA. Okay. I'm getting the length of WSA. Okay. It is 2 bytes. Now I am moving 5, 7, 8, 9. This is my value. I'm moving to WSA. So now I want to display the value of WSA. In the spool area, I can see 5, 7, 8, 9. Okay. Here 4 bytes only now I have initialize. So I'm passing 4
Yes.
bytes of value only. Okay. Clear everyone?
Yes, ma'am.
So how this value will be stored internally? Internal representation for comp. So what is the comp internal representation? It is binary format zeros and ones. Okay. So see properly 2 bytes. So see here how many bytes? 1 byte is equal to 8 bits, right? So
Yes.
here how many bytes I am getting? 2 bytes
2.
means 16. 8 into 2 16 bits. Okay, clear.
Yes, ma'am.
So I'm getting 16 bytes. You can count, these are 16 bytes. Do you know how this binary value we are getting? What is the formula for that? Hello? Hello? Gopal, Nikita, Shamala. Say,
Yes, ma'am.
do you know or not how this binary value we are getting?
Oh, yes, money.
So what is the formula for this?
Actually, we have done earlier. Hmm.
What Nikita is telling?
Nikita, tell.
I am not saying anything. Gopal only saying.
Like in the LCM only by the LCMs and the remainder we are calculating now. By that only.
So see here. So this is the formula 1. So 1 double 2, 2 double 4, 4 double 8. So 8 double 16. Okay.
Yes.
16 double 32. Okay. Like that we will represent. There is a formula to remember. So it is in where computational variables are used only for numeric. By using value class only no. So it follows right justification. We already know about this right justification. So I'm getting how many bytes of memory? 4 bytes. Is S9 of 4 is how many bytes? 2 bytes. Okay. 1 byte is equal to 8 bits. So for 2 bytes, 16 bits. Okay. So you can count these are 16 bytes of value. Now you already know this first 5 will be stored, 5 7 will be stored, 5 7 8 will be stored, 5 7 8 9 will be stored. You already know this process. Okay. Now I will explain only this how these zeros and ones are coming. Okay. So what is the value? First 5. So I'll keep 1 on 4 and in the place of 1 also I'm adding 1. So binary value is 4 by 4 digits only, no? So if I add 4 plus 1, I'm getting 5. So for 4 and 1, I'm adding 1. In the remaining two places, I'm adding 0. Then I'll get the binary value of 5. 0 1 0 1. I have written here also 0 1 and 0 1. So see for 7, so add 4 plus 2, 6, 6 plus 1, 7. So add 4, 1, 4 to 1, add 1 to the digits and 8, 0, 0 double 1, sorry 0 triple 1. For 7, it is 0 triple 1. For 8, simply I can add, there is a 8 now. So in place of 8, add 1. Before you can add zeros. 1 triple 0 is the binary code for 8. So for 9, you can add 8 plus 1, 9. So in between, you can add 2 zeros. 1 0 0 1 is the binary code for 9. Like that, you can write the binary values for these numbers. Understand?
Oh, yes, man.
So if you
Yes.
want, you can take a snap or else you can do.
Yes, man. You can.
So clear this example? Understand or not?
Yes, money.
So now declare one more variable S9 of 5 comp. So what is the range? It is 4 bytes. S9 of 5. It is 4 bytes. Okay. So 4 bytes means 4 bytes. See, 1 byte is equal to how many? 8
8
bits.
bits.
For 4 bytes, how many bits? For 4 bytes, how many bits?
Now,
Into 4,
Say what is the value?
30.
Hmm?
32.
Say loud.
Loud bolo, loud.
32 bits.
32. Okay. 32 bits only. So actually you have 32 bits. So my value is what? 18763. This is my value. I'm moving to WSA. If I display WSA, I'm getting 18763. Okay. What is the length? 4 bytes. What is the value? 18763. Okay. So each digit will carry 4 bits. Okay. So here how many digits are there? 5 digits. 5 into 4, 20. Understand or not?
Yes, ma'am.
5 into 4, 20. So I'm using only 20 bits are filled for 18763. Okay. All previous bytes do not have any default values. Means what is the, we are having 4 bytes of value, it having 32 bits, but you are using only 20 bits. So the remaining bits are not having any default values. Okay.
Yes, ma'am.
So see here, 4 bytes equal to 32 bits, but I am using only 20. The remaining bits I am not using, and there is no default values for that. Previously, if I in the value class and access statement, so there is the 0 is the numeric, 0 is the default value for numeric value class. In accept statements and alphabetics, you have default value is space, but here there is no default values. Okay.
Yes, ma'am.
So like this, four digits will be there for each binary value. And what is the formula? 8. So now what is the value? First one is 1. Okay. Now I can add in place of 1 and remaining zeros. Okay. 0001 is the binary value for 1. Next 8. So in place of 8, add 1 and remaining zeros. So 1000 is the binary value for 8. For 7, add 4 plus 2, 6, 6 plus 1, 7. So you can add 1, 1, 1 for 4, 2, 1, and this in this place you can add 0. 1111 is the binary value for 7. So for 6, you can add 4 plus 2 is 6. So in place of 4, 2, you can add 1, 1. So you can add 0, right and left. 0110 is the binary value for 6. If you add 2 plus 1, we'll get 3. So you can add 1, 1 for 2 and 1. Before you can add zeros. 0011 is the binary value for 3. Take a snap. Clear?
Yes, ma'am.
Yes, ma'am.
So understand about what is the internal flow of representation in the COM of binary values in the binary format.
Yes, ma'am.
So what is the main difference for this COM? Next, we completed the COM. Okay, up to here, this is COM. Now, COM 1 and COM 2. So both are
Floating point.
hmm, so internal floating point. Okay. So both are what? Computational variables. So in COM1 and COM2, data will be stored in internal floating point. So data will be stored after decimal points. Data will be stored after decimal points. That is internal floating point. Okay, if you see COM1 and COM2, so in COM1, single precision floating point. In COM2, double precision floating point. In COMP1, 4 bytes. The length is 4 bytes. It is fixed. In COM2, the length is 8 bytes. It is also fixed. There is no picture class for COMP1 and COM2. So it is important. In COMP1 and COM2, there is no picture class. So in COMP1, it will store it in rounded values or rounded results will be stored. In COM2, precise results will be stored. In COM1, the range is, you can write it from 0 to 22 decimal points only. After decimal, you can write maximum 22. For COM2, the range is 22 to 55 decimal points. Okay.
Yes, ma'am.
So you can see example on COMP1. So 01 WSA, there is no picture class. Directly you can write COMP1. So one more variable for displaying the picture class length for COM. Compute L equal to length of WSA. So memory of WSA at what? 4 bytes. So I already said that length of 4 bytes is fixed for comp1. So moving 897, sorry, 57890 to WSA. If I display WSA, so in the output I can see after decimal 57890 and remaining filled with zeros, and last I am getting E. E means what? Exponential. Okay. So in some systems we'll get E, and in some systems we will get like what is the length of value? 5. So we'll get 0.5 like that. So based on our emulator, the value will be changed. Okay, the last value. So here the value will be come at well compare like the value will be compressed and stored. Okay, in comp1. Coming to com2, so 01 WSA declare the com2 where variable declaration. So one more variable for picture class length. Compute L equal to length of WSA. Display WSA of memories of L is 8 bytes. So length of 8 bytes is fixed for comp2. Okay, move 57890 to WSA. So display the value of WSA means in the output area I can see after decimal 57890 and remaining are filled with zeros and E. It is a floating point. Okay.
Okay.
So here the value will be compressed and stored into COM2 variables. Understand?
Okay.
Yes, ma'am.